literally over the last 10 years or so, people have been proposing more broad-ranging, lower-level theories. And by lower level, I don't mean they're worse explanations. I just mean they're intended to just explain more of the symptoms of autism, but the deficits are at like a lower level of processing. So cognitive, something like theory of mind is a very high-level process, but these are affecting things that are less cognitive, less complex processes that our brain does. So just a brief reminder from yesterday, autism is this neurodevelopmental condition which is prevalent in about 1% of the population, and we have this triad of impairments, so social, communicative, and behavioural. Although the new criteria for autism puts social and communicative deficits together. We have the thing that we didn't really mention too much yesterday was these non-social symptoms. So we mainly focused on the social symptoms, how people struggle with theory of mind or social interaction, developing and maintaining friendships and relationships, that type of stuff. But we didn't focus too much on the non-social symptoms. And as we saw in the DSM, which is used in America to diagnose autism, we have these classic symptoms that autistic people must manifest at least 2 of these. So these stereotyped or repetitive motor movements, objects of speech, then this insistence on sameness, restricted, fixated interests, and as I mentioned earlier, yesterday, the strange reactivity to sensory input, or unusual interest in sensory aspects of the environment. So we need a theory that can explain both, and none of the theories that we've put forward so far seem to have been able to do that. So as I said, people have been looking for deficits at like a lower level of explanation, essentially. I think possibly the most classic one that people think about nowadays is called the broken mirror theory, and this developed out of research into mirror neurons in the 90s and early 2000s. So basically the idea is that autistic people have a dysfunctional mirror neuron system which underlies the impairments that we see in them. And don't worry, we'll explain what mirror neurons are on the next slide. The idea is that abnormalities to this system impair imitation at an early age, and this subsequently affects the later development of theory of mind, producing characteristic autism deficits. So as I said, I'll explain what mirror neurons are. They're these visuomotor neurons. So by visuomotor, I mean they fire both at visual input and at motor input, essentially. They discharge both when an agent, when a human being or a monkey, or potentially other mammals as well, perform a particular action, and when they observe another individual performing a similar or the same action. So mirror neurons were created, you can see these are Italian names. They kind of came out of Parma Group, a group of researchers based in the University of Parma, and it's been taken and ran with by the Italians, essentially. But this is a good example to show what it is. So for instance, when the monkey's at rest, it's not doing anything in its hand, the mirror neuron doesn't fire. When the monkey grasps the ball, the mirror neuron fires because it's a motor neuron, and motor neurons are the ones that discharge in order to activate muscles in the hand and the wrist, for instance. But also, the mirror neuron fires when the monkey sees someone else. You can see someone else is grasping the ball here, doing exactly the same action, and the mirror neuron fires as well. So it fires both when the monkey grasps the ball and when it sees someone else grasp the ball, whether that's human or another monkey. And basically, when people discovered this in the early 90s, the classic reference is Di Pellegrino 1992. Essentially, there was a lot of hype about mirror neurons, and if you see in the decade, 15 years or so after that, they were kind of put forward as an explanation for culture, for action understanding, autism, theory of mind, empathy, so many different things, without too much evidence in favour of it. Anyway, going on to the broken mirror theory, it basically makes 3 assumptions that we'll go through one by one. So the first one is that mirror neurons facilitate imitation in some way. The second one is that imitation is then required to develop this theory of mind ability, and theory of mind being the ability to ascribe mental states such as beliefs, desires, thoughts, intentions to other people and oneself. And then the third one is that individuals with autism have a dysfunctional mirror neuron system. And all 3 of these assumptions need to be met for this theory to work. So first of all, do mirror neurons And I think this is the best supported of all of these assumptions. So human mirror neuron areas appear to be quite important for imitation tasks. So we found mirror neurons in 2 parts of the human brain, 2 parts of the monkey brain, in fact. Most of the research has been in monkeys and rhesus macaques, which are typically used in psychology research. If we wanted like a proxy of humans, but without experimenting on the brains of humans. So, although I think this research is human research. So there was this study in 2009, and they got participants to intentionally imitate finger movements or hand movements. So you can see here, this is what they have to do to imitate hand movements, and then down here, these are the finger movements they have to imitate. So someone would be sitting or standing in front of the participant and say, doing that, and then they would have to do exactly the same back. And they found lesions, so injuries, to the inferior frontal gyrus. So remember, the inferior frontal gyrus is kind of like inferior bits in the frontal lobe. It causes attention neglect in many cases, led to significant impairments. And we also have this study by Kat Moratel. I think she's at UCL now as well, which is automatic imitation paradigm. And this is a really interesting paradigm in psychology and in imitation research, because most imitation work, for instance, the Goldenberg and Carnath work, people consciously and deliberately imitate the actions of others because they've been told to do that, right? So someone puts a hand like that, and then you get told, do the same thing yourself. It's very conscious, it's very deliberate. But automatic imitation is different. They make people automatically imitate the movements of others without really realizing it. So the idea is participants are instructed to open or close their hand whenever the hand on the screen in front of them moves. But the displayed hand can be either open or closed, which means that some participant movements are unintentionally imitated, whilst others aren't. So you can best see this on the diagram on the next page. So here, some participants have been told to close their hands when they see the hand on the screen in front of them move. So if the hand closes, then their reaction is imitative. If the hand opens, it's not imitative, they're doing the exact opposite. Others have been told to open their hands, so this is non-imitative when they see the hand close, but it's imitative here. So the idea is that some of the actions, they do imitate the hand they see on the screen, and others they don't. But it's not deliberate as to which one they're doing, essentially. And in this study, Kat Moratel used TMS. So TMS is transcranial magnetic stimulation. It's a way of stimulating the brain using basically, I've not done this before myself, but it's like magnetic stimulation. So you fire magnetic impulses into a certain part of the brain. You can get very precise in how much you direct it or where you direct it to the IFG, which is the inferior frontal gyrus, which is where we find mirror neurons in monkeys. And we found that this automatic imitation of finger movements was disrupted. So you can see here the TMS, transcranial magnetic stimulation. They did it. They had a baseline here where there was no TMS tool. They did it with the inferior frontal gyrus, and then they did it with the PPC, which is the posterior parietal cortex. That's like a controlled condition. And you can see that the imitation effect was much stronger. I think this is the difference between the open and closed conditions. And you can see that the effect was much stronger in the IFG condition, essentially. Although I probably need to get back on that diagram because I'm not entirely sure what the colours are. But you can see big differences there, regardless. And so the second assumption was that imitation is required to develop theory of viability. I think this is slightly less well supported, but there is some evidence for it. So for instance, we go back to Meltzoff, who conducted that classic study, Meltzoff and Moore, 1977, with the babies who were 3 weeks old. And Meltzoff argued that imitation, because Meltzoff is the imitation man, if you're doing any psychology research or looking at any psychology research, his name is going to get mentioned. And his theory is essentially that imitation is crucial for all of our later social processes. But he basically argued that, yeah, imitation provides this crucial basis for recognizing the associations between observed actions and mental states, so implying this important role in theory of mind, essentially. And he makes this circumstantial argument, and the circumstantial argument, he doesn't have any empirical evidence for this as such, to start with, but his first argument is that there's like this very obvious functional resemblance if I'm imitating or if I'm ascribing beliefs to other people, they require me to translate from the perspective of another individual to myself. So I'll explain this in better detail. In imitation, I must convert another person's actions into my own actions. And in theory of mind, I must copy the beliefs, convert the beliefs of another person onto my own brain, right? So in both cases, you have to translate from the perspective of another and somehow take it on yourself in some way, in both imitation and theory of mind. So they argue that the two they functionally resemble each other, and therefore it's to some extent logical that theory of mind might arise out of imitation. And so there was this study by Young et al. About 10 years ago, and they didn't support this. So they found, you can see on the graph of the next slide, that infants who later developed ASD. So the way we can do this is we can take a huge cohort of children, of infants, and some of them are more likely to develop autism than others, because as we said, it's a genetic condition. And if they say have an older sibling or a parent who's got autism, then they're at much higher risk of developing autism themselves. And they basically found, you can see here, we have low and high risk typical people, and then people with autism. The autism group is down here. And you can see that this is an ability estimate, like an imitation ability estimate. And you can see that they are worse at imitation, but it's just that they're delayed as such. And therefore, if you go back, the people who develop autism, clearly, as we discussed in the last lecture, struggle with theory of mind, they're impaired at theory of mind. But their imitation isn't necessarily worse as such, especially when they get to later life. It's just been delayed within childhood. So it's not like the idea is that imitation can't be causing these theory of mind deficits, because the delay wasn't associated with these different developmental trajectories. Essentially, there was no positive or qualitative difference between the trajectories. And yeah, the imitation delay wasn't autism specific, because if we go back, you can see that for instance, other clinical groups, which is this dotted line, also have imitation delay, and even the high risk typical people, so the ones who are in the high risk group, the ones who have family members who have autism and don't develop autism themselves, also have a slight delay in the development of imitation, which suggests that imitation impairments don't lead to theory of mind deficits, as I said. And finally, the third point, which is the one that's probably being most debated, is the idea that individuals with autism have a dysfunctional mirror neuron system. And this is, as I said, has been debated, but automatic imitation appears to be quite normal in autism. So Cook and Bird. So Jeff Bird, he's the second author here. He was my main tutor at Brasenose in Oxford, which is my college in Oxford, and Cook is actually his wife, Jenny Cook. Lovely people. There's Jeff, he's at Brasenose, that's my college in Oxford. There's me and Jeff. And they found that reaction time for autistic people is actually faster during the congruent imitative trials than the incongruent non-imitative trials, which is exactly what you'd expect to find, right? In automatic imitation. And there was no difference between autistic participants and neurotypical. So you can see the graph here. Ignore this, what's this? Magnitude imitation. Ignore this one over here. They did a slightly different manipulation, which was about sociality rather than imitation. But these ones here, ASC, autism spectrum condition, and you can see that their imitative magnitude of their imitation is virtually exactly the same as this control. The control participants, when the automatic imitation task was non-social, there was no social evidence to it. And another way we can index mirror neurons in humans is by mu suppression. So this is quite a complex thing to get your head around, to some extent anyway. But EEG here, electroencephalography, is one of the key it's one of the key measures we have of recording the brain, and it's a way of recording electrical signals from the scalp essentially. And it's good in some ways because you get really fine-tuned timing of when the brain is active. So for instance, you can get it within the classic electrical signal that comes from the brain that people study quite regularly is called the N170, and that occurs within 170 milliseconds of the stimulus being presented, like for instance a face. So it's really good in terms of time course, but it's not necessarily fantastic in terms of locating where the signal is coming from. Anyway, it's one of the techniques that we have to measure brain activity. And one thing the EEG is good at, as well as picking up individual spikes of electrical activity from the scalp, is it picks up rhythms in the brain. So for one reason or another, the brain has these rhythms of activity, of electrical activity, that go at different frequencies. So we have alpha, beta, mu rhythms, and the one we're looking at here is mu. So the mu rhythm in the brain occurs at like a frequency of 8 to 13 hertz. So we get this activity, if we record from the brain, at 8 to 13 hertz. So it happens 8 to 13 times a second. And we, the researchers record this electrical rhythm from mirror neuron regions, so as we said, the inferior frontal gyrus, for instance, and also the PPC. And in neurotypicals, which, non-autistic people, the power of this new signal is suppressed both when executing actions and when observing the actions of others. So it's considered an index of the integrity of the mirror neuron system, which is obviously not presumed to be dysfunctional in neurotypical people. Please ask me questions if I'm explaining this a bit too quickly, but to simplify, there's a rhythm within the brain that we can measure of electrical activity, and in normal people gets suppressed, which is used to index the mirror neuron system. And then we have a study by Autism et al. And basically you can see here that in controls, it's suppressed when, what's this? Yeah, this is compared to a baseline. And when they're watching someone's hand move, for instance, when they're watching someone's hand move, then it's suppressed in controls, but it's not suppressed in these autistic participants. You can see these are confidence intervals, and they overlap with baseline, so the idea is that there's no difference in that condition. So they basically, the ASD group showed the significant use of pressure to self-performed hand movements, but not to observed hand movements, if we go back. So you can see here, they do get the use of pressure when they move their own hands, the autistic participants, but not when they see someone else move their hands. So the idea is that their mirror neurons aren't firing as well as neurotypical people when they observe other people grasping a ball, for instance, or moving their hands in the same way. However, this evidence has been criticised. So, for instance, more recently there's been this meta-analysis, we talked about meta-analyses before, by Hamilton, who's at Nottingham in the UK. And basically, there have only been 5 studies looking at use suppression, and none of them reported the hypothesized interaction that would have shown this result. So you can see here, it should be revealed in the group by condition interaction where participants with autism show suppression in the performed action condition, but not in the action observation condition. Of the 5 studies, none report this conclusive interaction. And without boring you too much with the statistics, you can see here that the controls do show suppression when they observe someone's hand movement, and the autistic people don't. But this is only in these simple effects with the effect sizes here with the confidence intervals, and you don't actually get an interaction between the two. If you compare these two groups, there's actually no significant difference between the autistic group and the control group in the hand condition. These are different electrodes, by the way. So for instance, C3, CZ, and C4 are all different electrodes that we're recording from the scalp. When you have an EEG, you probably put normally 32 or 36 electrodes onto the scalp and record different parts of the brain. You can see here they have this effect, as I said. You have simple main effects, but you don't have an interaction effect, which would be the effect that you're looking for, essentially. So people have essentially extrapolated from these results far more than they should have done. Is everyone with me? If anyone has a question, please ask, because this is quite complex statistical stuff. Okay, we're good. And then we have this paper by Hobson and Bishop. So Dorothy Bishop, she's also at Oxford. She's been at Oxford for decades. She's an absolute genius. She writes her own novels as well, as being an incredible psychologist. And Hannah Hobson, she also did her PhD at Oxford as well. But they did this paper looking at view suppression as a good measure of the human mirror neuron system. And they argued that this effect was easily confounded with alpha suppression. So as I said, we have different rhythms in the brain. One of them is the mu rhythm. We also have an alpha rhythm, which is like, if mu is 8 to 13 hertz, alpha I think is something like 3 to 7 hertz, so it's in the next category of rhythm essentially. It's almost at a similar level of hertz to the mu effect. And basically the alpha suppression, the alpha rhythm, is confounded by attention, so the alpha rhythm changes depending on how intense our attention is. And they basically said the mu rhythm isn't confounded by differences, it is confounded by differences in attentional engagement across the different tasks. Basically, when they're in the baseline condition and when they're performing the action, they're concentrating more on the action condition than the baseline condition, which is leading to these effects. As I said, the mu suppression was only found when comparing against the static baseline stimulus rather than dynamic. So with the static stimulus, you'd expect less attention to be allocated compared to a dynamic stimulus. You might want to read that paper because, again, this is quite a complex conclusions to draw from this. The idea is that the mu rhythm is actually getting confused for a different rhythm. And then we have fMRI data. So remember, we mentioned the other main way of recording from the brain is called fMRI, and that's when we measure the oxygenation level in the blood, and parts of the brain that are getting activated should have more oxygen in the blood than parts that aren't being activated. And this is kind of used as in partnership with EEG to some extent, because fMRI is really good at telling us the location of brain activity, but it's the time course is really bad. As I said, we have to wait normally something like 6 seconds from when the brain activity is to when we can see it recorded, but it's quite variable. So the time precision is low, but the spatial precision is high, whereas EEG, time precision is very high, whereas the spatial precision is low. And this is Hamilton's meta-analysis again, and basically they found just 2 of the 8 studies that have been looking at fMRI in the mirror neuron areas as people, as autistic people and control people, like activate the mirror neuron system in some way. Just 2 reported significant differences between the 2 groups, and these results contradicted to each other. One reported increased activity in the inferior frontal gyrus, whilst the other reported decreased activity. So basically, there's no strong evidence that autistic people have a dysfunctional mirror neuron system, would be my conclusion. That's the end of the mirror neuron bit. As I said, if anyone has any questions, because I went through that quite quickly, and it was very neural rather than psychological. So I'll wait for a few seconds if anyone does have any questions. No? Maybe I've just confused you all. But it's a really interesting area. Anyway, kind of related to the mirror neuron system, but not really, is this motor atypicality theory. So this theory basically suggests that autistic people, stay with me here because it sounds quite wild, but their symptoms are based on motor deficits. So one of the key symptoms of autism, which we haven't really talked about at all so far in the last lecture and a half, is that autistic people tend to move and have atypical motor activity. And I'll show this in some evidence in the next few slides. But this theory was proposed by Cook, so this is Jen Cook, that's actually Jeff's wife. So I've met her a few times. I was at her wedding actually. But anyway, she basically theorized that one's own movements influence the interpretation of others. So if our own movement is atypical, then the interpretation of others' actions will be impaired too. This is the logic. And so these motor abnormalities may compound social interaction in autism essentially by, in one way, the autistic people struggle to interpret the actions of neurotypical people, but in another way, non-autistic people who interact with autistic people may not be able to interpret the movements and the actions and intentions of the autistic people. So it leads to kind of like this vicious cycle almost, or it's one effect is compounded by the other, because autistic people struggle to understand non-autistic people, and non-autistic people struggle to understand autistic people. And so they're basically operating at different levels, and there's no common ground there to work from. So this essentially hinders successful communication during social interactions. Is everyone with me with this theory? Yeah? have motor atypicalities. So there's this study in the early 90s which looks at posture and balance in autistic people compared to controls. And you can see here, in comparison to normal children, the autistic subjects were less likely to exhibit age-related changes in postural performance, and postures were more variable and less stable with more lateral sway. So basically their postures are worse, and they're less stable and steady on their feet essentially when we measure this. I won't go into the actual methodology. And also autistic subjects paradoxically exhibited greater stability in more stressful postures, such as you can see here, putting excessive weight on one foot, one toe, or one heel. So these are things that neurotypical people don't tend to do, or autistic people do, and because of some idiosyncratic mechanisms or increased practice that neurotypical people don't normally do, they actually end up feeling more steady in postures that aren't particularly comfortable. Then we have macrographia. So macrographia basically just means large handwriting. And this is taken from autistic persons. They just have to draw swirls, I think. And you can see, this is in centimetres. You can see they have really large handwriting. They just told to do these swirls. And in fact, taken from the same paper, this is the vertical size, so the average distance between the bottom and the top of the character that someone's writing. And you can see the autistic group, the ASD group, is much larger than the typically developing group on average in terms of the handwriting. And in fact, some people go way up there. This is a box plot, so this is where 75% of participants in the ASD group have handwriting lower than that, but it's like half the size in the typically developing group, if not less. So basically, autistic people have large handwriting, which is another motor abnormality. And they also have abnormalities in upper limb functioning as well. There's so many others I could quote, these are just 3. So autistics tend to make jerky arm movements, which proceed with greater velocity and acceleration, which is a signal of jerkiness essentially, which contrasts with this minimum jerk profile, normally displayed by neurotypical. So the point of this research is that when we move, if we're not autistic anyway, then typically bodily actions they unfold with a minimum jerk profile, which means we don't move in a jerky way, we move in a smooth way. Even when I'm just doing this now with my hands, it's smooth, it's not jerky. And you can see here from this study, which Cook did, this is a measure of jerkiness, this is a measure of acceleration, and that's a measure of velocity. Red is the autistic group, blue is the control group, and you can see all they had to do was just swing their arm like this, right? It's not a very hard action, that's all they were told to do. And in such a simple, in fact you can see what they're having to do here, it's at the bottom, but just measuring from different electrodes I think placed on the arm, you can see that they move in a much jerkier way and with much greater acceleration. So how does this link to actual understanding? Well, one way we can think about it is motor resonance. This is similar to, as I said, this is similar to the mirror neuron stuff. So overlapping activation of the motor system when both observing and performing actions, which, as I said, is the basis for the neuronal system. And it requires similarity. So observed movements should strongly activate the observer's motor system, but only if they're congruent with actions that the observer can actually produce, so actions in the observer's motor repertoire, right? If I'm seeing an action, but I can't do it, so for instance, the example that we're going to come up with, you'll see how it works, then I should have my motor system activated. So as I said, what activity would provide a good test of this hypothesis? Something that we can see all the time, but some of us aren't really good at doing, including myself. Any ideas?
Teaching.
Pardon?
Teaching.
Teaching? You're saying I'm not very good at teaching?
No, I'm saying you are good at it.
I said I'm not very good at it. But anyway, anyone else? It's not teaching. It's a motor activity. Not cricket. I'm not good at cricket though either.
Yeah.
Okay. It's dancing. So we see it all the time, but many of us aren't very good at dancing, as I said, including myself. And so therefore, if I see Uma Thurman and John Travolta dancing on screen, I'm like, right, they're way better than me, so my motor system shouldn't be activated because I can't do what they're doing. Is the point. And so this was studied by in 2006, and they actually had dancers, like professional dancers in training, and they were trained these new complex dance moves, and then they observed the dance move performed by someone else, like an expert on video. So you can see here, they had these actions, these are control actions, so these are ones they haven't been trained in, and experimental actions, which are ones they have been trained in. And motor resonance, which we measured as a Bolge response. So Bolge response is just the measure we get from fMRI studies, so the blood oxygen level dependent response. We get it from fMRI, but motor resonance co-varied with the function of the dancer's self-reported ability to execute each move. So essentially, we found increased response in the motor areas of the brain to activities that the dancers could perform, and reduced response in motor areas of the brain to dance moves that the dancers couldn't perform, or weren't very good at performing. Which is an example of actions being perhaps understood, or at least having different neural correlates in your brain, depending on whether you can do them or not. And you can see this is the past of the brain, so this is past activated. That's actually a monkey brain, but I don't know why I put that in. Yeah, therefore one's own motor repertoire may moderate the encoding of movements of others, essentially. Does this all make sense? Are you with me right now? That we encode movements better if we can do them of other people. And then there was this other study. This is a really cool study, 2012. And it had two different elements to it. So the first part of the study was an action execution task. And participants, they were given this visual discrimination task, a perceptual task. And they were presented with this very basic visual stimulus. These are Gauss filters, or Gauss filters, I think. And then there was a time interval, and then they were presented with the same stimulus again. And they had 2 seconds to decide. They were told to look for something in these tasks, and it was very difficult. It was a really difficult visual discrimination task. But for instance here, this one was slightly stood out more than the other 5 stimuli on the screen, whereas here they were all exactly the same. So in one of these 2 stimuli, visual stimuli, there's an odd one out essentially. And participants were told, they were given a 2 alternative forced choice task, and they said, was it the first stimulus or the second stimulus where there was an odd one out on the screen? But it was a really difficult study, and they gave their confidence intervals down there, but at first they had to say which one it was, and then they had to say, then they had to give their confidence and their judgment on a 1 to 6 scale. But in addition to giving an explicit confidence judgments on like a 1 to 6 scale, they also had to put a marble in the slot. So they were given marbles on the table in front of them, and they had 2 slots. So if they thought it was in the first stimulus, the odd one out, then they had to put it in the left slot. If they thought it was in the second stimulus, the odd one out, then they had to put it in the right slot. Okay. As I said, in addition to making these explicit confidence judgments, participants could place the marble into a slot to indicate whether the target appeared in the left or right percentage image. Or sorry, first or second. And as expected, the authors found increased confidence was associated with faster movements. So if you're more confident in your judgment, you're going to be like, okay, there's the marble that's going in there, right? If you're not sure, you might wait for a little bit, and you might be like, I don't know, and then put it in one that maybe you have slightly more confidence in. So this is something you'd expect to see. If you're more confident, then you're going to put the marble in the slot faster, right? Everyone with me? So you can see here, this shows this mean confidence level. This is time, and you can see that the more confident people were, the less time they spent putting the marble in the slot. Then, after the action execution task, there was an action observation task, and participants observed videos of others doing the action execution task, putting the marble in the slot. And they found that the judgments of others' confidence levels were related to participants' own judgments for their own movements, essentially. So movements by the actor, the person that you're observing, that were judged as confident, tended to be similar to one's own movements that had previously been judged as confident by oneself, essentially. Does this make sense? You can see here, mean inferred confidence is correlates with the predicted mean inferred confidence from one's own actions. And basically, they argue, these authors, that mental state inference, which is the signature impairment in autism, as we said, may also be affected by the meanings attached to one's actions in one's own motor repertoire. So the idea is that if autistic people have abnormal movements, which we established at the start, then the inferences they make about other people's movements may be affected in turn because their own movements are abnormal. Yeah, that makes sense. And finally, with this motivated health theory, it's really interesting because, as I said, it's not just that neurotypical people is that neurotypical people may also struggle to understand autistic people if they have abnormal motor functioning. So motor deficits compound social interaction problems by preventing non-autistic interactors from inferring the motives and intentions of their autistic counterparts, which hinders successful bidirectional communication. So this is a cool study done again, I think, in UCL. UCL is an extremely good psychology department that used the Frith-Lappé triangle animation test. So I'll explain this for you. This is the Frith-Lappé triangle animation test. And it should be playing. Please play. No. Okay, I don't know why it's not playing. Oh, I have to enable content. So essentially the idea is that people get given two triangles and they have to use like magnets underneath the table to move the triangles around in such a way that it acts like a social situation. Obviously the triangles are triangles, they're not social. But you can see, you can ascribe belief. So I think this one is persuading. Quite sweet. But anyway, the point is that the task is, you can see this is how it works. They get given two triangles, and underneath the table are magnets, so you can put the participant can put her hands underneath the table and move the triangles around because of the magnetic force. And from this they need to act out. They were told to act out coaxing, mocking, seducing, and surprising. And then use the triangles to represent what they were trying to do. And they found the movements, when they had an autistic group and a neurotypical group, they found the movements of the autistic participants, as we'd expect, were significantly jerkier than the neurotypical controls. So this is movement jerkiness, and the autistic group is in red, the control group is in green, and for every single one of these things, the jerkiness of the autistic movement was a lot greater, which is obviously not great, because, as I said, control people, neurotypical people tend to have this minimum jerk profile to our movements. And because of this, the argument is that these neurotypical control group struggle to understand the meaning of the autistic animations, because then after they produced these animations, they waited a few weeks, got the participants back into the testing room, and they then got them to interpret. They got them to ask, okay, which word are they acting out here? And they presented them with the videos or recordings of the triangle tasks that have been created by both autistic and non-autistic participants. And you can see here, individuals with autism struggle to interpret animations irrespective of the generator, so their mean rating accuracy was less than 6. They got less than 6 out of 10 right. Whereas the typical controls here are fine, they're really good at and really accurate at working out the meaning of the animations created by other neurotypical people, but they're not very good. In fact, they're worse than even autistic participants at working out what the autistic participants were trying to represent with their triangle animations. And deficits were associated with the jerkiness of the animation. So you can see here, the rating accuracy massively decreased, massively increased as jerk decreased, essentially. So the jerkier animations were more difficult to interpret. And so therefore, yeah, people find it difficult to interpret animations that move differently to their own movements, whereas ones that move in a way that is similar to one's own movements are easier to interpret. And this basically implies that neurotypical people may struggle to anticipate and predict the goals and intentions of an autistic interaction partner, which leads to inappropriate and inconsistent feedback during social interactions, which then leads to like these downstream effects. So autistic people, their already existing effects may be compounded because they're not understood by 99% of the population. Okay, so I'll give you a break there because I've gone through a lot of content again. But as I said, if anyone does have any questions, please do let me know.
Apologies if I'm asking you to repeat this one. Can you define abnormal?
Abnormal in what way?
You said that people differentiate between normal and abnormal.
I think abnormal is quite a loaded term. The word we normally use is typical, so we say...
I'm just going to try to turn this down because it's...
Oh, is it really annoying? So yeah, the word we normally try and use is like neurotypical and neuroatypical. I wouldn't try and use abnormal that much, maybe I have accidentally. But normal, I guess, normal is something that we'd use in more like a frequency way. So it's not saying, oh, you're abnormal, therefore you're strange, and we're going to judge you for that. It's more like your behaviours aren't what we'd expect, or they're not very high frequency within the general population, essentially. Does that make sense? We try and use like less loaded language. Any other questions? Yeah?
This may be a lame question, but
A lame question?
yeah.
Go on.
So when you talk about posture and balance problems, action, execution, and observation, do we see these features developing or maybe increasing in severity over a period of time, or that's something which is just inherent since birth?
I don't know. So some of the research that I've looked at has shown balance problems at like a very early age, posture and balance problems, motor problems at a very early age in people who then later go on to develop autism. Whether there's a developmental aspect to it, I would argue that there possibly is, because as I said, it gets compounded. So maybe if you're worse, if you have already existing balance, posture, motor problems, then maybe they are going to get compounded because you're not receiving feedback that you'd expect, which non-autistic people probably do get. But to be honest with you, I don't really know the literature on that so much in terms of the developmental trajectory. I just think that, yeah, there has been a huge body of literature showing these posture problems, especially in autistic adults, but also in autistic children. So it does seem to be present from quite a young age. But as for the developmental trajectory, I'm not entirely sure. Sorry.
Just one question. When you say that autistic people struggle with predicting the goals and intentions of neurotypicals,
Yeah.
do they find it relatively easier to maybe do the same with other people who are autistic?
No. You can see here there's no difference. So they struggle, with this task in particular at least, they struggle to infer the meanings of the typical generator, but also they don't do any better with the autistic generator either. So it's not like autistic people can understand each other. And I guess partly that's because there's so much heterogeneity and variability within autism that like one autistic person is completely different to another one to some extent anyway. So they're just going to struggle regardless of whose actions they're interpreting.
I had a question. So, like, you know, the whole imitation theory, right?
Yeah.
The thing, can't it be like, look, you know, the reason why autism occurs not because of, you know, a problem with imitation, but in fact there is a problem with imitation because there is a problem with theory of mind, and the old theory of mind theory can be...
I don't think so, because imitation develops much earlier than theory of mind. Imitation, as we said, is present, maybe not at 3 weeks, but it's present very early on in childhood, whereas theory of mind typically develops, the ability to pass a false belief task typically develops at 4 years old, so years after you develop the ability to imitate. So it's not like theory of mind can aid imitation, it's more like imitation then leads to theory of mind as the theory anyway, which I don't necessarily agree with. But yeah, it's not like theory of mind can lead to this imitation deficit. Okay, we'll move on. So a final theory that I really like this theory, is the social perception theory. So before I go directly into this theory, I need to talk about weak central coherence theory, which is kind of the forerunner to the social perception theory. And this was created by Uta Frith, who's also at UCL. UCL's got so many, like its autism research is just on another level. And basically, she used this concept of central coherence, which is essentially this tendency that most neurotypical people have. It's very natural to process information within its context to gain higher level meaning. So we've talked about context in some of my previous lectures, and as we saw, people tend to integrate that context to make their judgments, right? But central coherence is this idea that we process information within its context, but we kind of lose memory for detail as such. So if we've just taken part in a I don't know, like a hazy party where we've been drinking a lot, we might remember the narrative of how the night went, but we're not going to remember the exact details of what someone said or exactly what they were wearing. We just remember, oh, he was saying nasty things to her, or he made out with her, that type of thing. We remember the narrative, but we don't remember the detail. And as I said, it produces this bias towards, that should say global rather than local processing. It should be the other way around, sorry. So Kanner was the first guy to look at autism. He was the first to define autism in the 1940s. Before the 1940s, it wasn't a thing. Well, it was a thing, but no one had defined it yet. And he made these early descriptions of autistic people. So he said that they had an inability to experience wholes without full attention to the constituent parts. You can see here, if the slightest, this is from Kanner's notes in 1943, if the slightest ingredient is altered or removed, the total situation is no longer the same, and therefore it's not accepted as such, or is resented with impatience or even a reaction of profound frustration. The inability to experience wholes without full attention to the constituent parts is what he talks about here. So the idea is that they look at things in their little details rather than the global, wider profile, essentially, of the whether it's perceptual or narrative or cognitive. So we have evidence for this from autistic people, visuospatial tasks. So again, this is Uta Frith's work, and they had the embedded figures test. So in this test, participants must find a hidden shape within a drawing, which is kind of masked in some way. So you can see here, these are two examples from the test. And in one test, they must find this house figure, and you can see here the house is there, but it's kind of hidden because we've got the rocking horse. And here we need to find the triangle, and the triangle is, can anyone spot it before me? Where? Top right. Maybe I don't have the, oh, here. Yeah, that looks different from my view. I'm sorry, that's my excuse anyway. But yeah, you need to find these hidden shapes within like these broader stimuli that are more detailed and complex. And basically, individuals with autism are really good at doing this. They're really fast at locating the hidden figure. So you can see here, the mean accuracy of autistic people was higher than normal people, and they called them mentally retarded. We wouldn't use those words now, but like a control group with intellectual disability. And they're faster too. And then we also have evidence from the block design test. So in this test, participants must arrange blocks to match a designated pattern that's been pre-designated. So here you can see they get given these blocks, and they're red and white with different bits of red, and different bits of the blocks are covered in red, different bits are covered in white. And they say you have to match this pattern up here. And so you have to put the blocks in such a way so that it matches that pattern, essentially. Everyone with me? And again, you found that autistic participants perform consistently better than controls. So you can see here, the autistic group, high IQ autistic, performed extremely well, even better than the young normal and old normal. So the autistic people performed even better. And even if we just compare amongst low IQ and split it like that, the low IQ autistic here perform better than low IQ non-autistic. So autistic people are good at doing these tasks that require essentially looking for details or working out details of shapes and things like that, visuospatial shapes. So it's likely due to this increased segmentation ability that they have. You can see here that there's controls gained an advantage, so the difference between control and ASD groups was reduced when the pattern had been pre-segmented already. So when they presented the pattern but with the blocks already shown in the pattern, so if I go back, they would have been presented this, but with the different blocks already in place, so they just had to recreate it. And in that case, the control neurotypicals did much better. You can see the advantage decreased. We also have perceptual evidence for this from visual illusions, which is really cool research. This is Frankie Happe, who's at King's College London, and there was this visual illusions test. So you can see here, one of them is the Titchener circles. I'm sure many of us have seen these illusions before. There's the Muller-Lyer figures, where these are the same length, even though one looks much bigger. The Titchener circles. So as you can see, that is exactly the same size as that, but it looks much smaller, for instance. And some of the other ones over there, like the Kanisa triangle. Interestingly, just as an aside, Titchener, this is Titchener. He was at Brasenose as well, so we have some cool alumni. But basically, they found that individuals with autism were generally far less susceptible to visual illusions. They don't fall for these visual illusions as much. You can see here, in every single one of these, apart from, strangely, the Muller-Lyer illusion, which is strange, the people with autism, what's this? Yeah, frequency data. So the extent to which they succumb to each illusion, you can see autistic people succumbed far less often to to Ponzo, Knisa, Titchener, Herring, and Poggendorf illusions than the people with mild learning difficulty and the normal participants. So they don't fall for visual illusions as much. However, weak central coherence theory, it was really big back in the 90s, but it never really took off because it doesn't really link with theory of mind and mentalizing performance, so it can't really explain that in some way. So it suggests that they're functionally distinct, the mentalizing abilities and the central coherence impairments. And it only characterizes a subset of the autistic population. It's not really universal, a bit like the theory of mind deficits. It's not universal across the autistic groups. Like some people aren't actually that good within autism. It's also underspecified. I won't get into that, but we don't really understand why at the cognitive and neural level this happens. So instead, people have kind of built upon this theory and looked at social perception, or, well, at first they looked at social perception, but then they looked at more broad perception. And basically the idea is that social perception deficits underlie motor abnormalities and their social effects in autism, for instance. So we can see here these point light displays. This is a point light display. Essentially, they're called Johansen figures. We use them in psychology quite a lot. And you just have these dots of light, but they get moved in such a way to depict movements and actions which we can attribute mental states to. So you'll see here, I'll ask you that question. What do you see in each of the following patterns of moving lights? Yeah, it's a person walking, right? But these are just lights. They're just dots on the screen. I think that's someone using like a sledgehammer or something like that to bash something. Arm day at the gym. And then I could keep going through the video, but the point is you can see certain actions from essentially what is just white dots on the screen. And Jen Cook again, they basically looked at what they did. They had these Johansen figures, but they varied in fact, no, this is a different study. But essentially, yeah, autistic people are worse at working out the actions of those Johansen figures. And we can see this in a similar study, because this is Jen Cook again. And what is it? Yeah, the velocity profile of movement was varied between 100% natural motion, so minimum jerk for a hand, and 100% for the ball. I'll explain this on the next slide. So, the participants, there was an autistic and a control group, and they were given either a ball, like a tennis ball, that was bouncing, or a hand that was moving in some way. And the manipulation was they varied the movement profile of both the ball and the hand. So for the hand, it varied between 100% natural motion, minimum jerk, which is what neurotypical people tend to do. We move our hands smoothly. And for the ball, it was varied between 100% gravitational, which is how you'd expect a ball to move, right? And 100% constant velocity, which is not how you'd expect a ball to move. You expect a ball to lose its velocity as time goes by, right? Because it loses energy. So essentially, they had the hand and the ball. One's social, one's non-social, and in some cases they were moving really strangely, not how you'd expect. In other cases, they were moving naturally. And participants were forced to judge which animation was less natural in like an adaptation paradigm. As you can see here, relative to controls, the autistic participants require greater differentiation between natural and unnatural motion to distinguish between the two. So this is the minimum jerk condition, and essentially this is the autistic group, isn't it? Yeah, and they needed the motion to be 40% minimum jerk in order to differentiate between natural and unnatural, whereas the control participants only needed to be 30%. Whereas there's differences here. In the ball, the autistic participants actually do better. Their performance is much better at working out whether a ball movement is natural or unnatural. Whereas when working out whether hand movements are unnatural, they're much worse. Which implies reduced sensitivity to biological motion. This is a perceptual deficit, right? But it could be linked in some way to their motor deficits. We have another study as well by 2003, Blake et al. And they basically had two visual perception tasks. So one was non-social. they just had to detect hexagons in a display of random lines. So you can see here, here's the hexagon. Can everyone see that? And some of them were harder than others. So this was an easy task, and this was a harder task. I can't actually remember where the hexagon is here. I think it's up here. So because there was more, you know, they varied it by how much difference there were between the lines. But I think this is the hexagon you're meant to find in this task. And then they gave them a second task, which is social. So detection of, as I said, biological motion from these point light displays from the Johansson figures. So these are just stills from it. They would have been moving, obviously. But you had to look at the biological motion. So this, I don't know what this was, someone walking. And then this is just random scrambled dots that don't show anything. And they found that the autistic group were unimpaired at the non-social task. So they could do the hexagon task perfectly fine. But they were really bad at detecting human activity from the point light displays. You can see here. This is a measure of sensitivity, D prime. And the normal people are much more sensitive at detecting biological motion from the point light displays, but there's no differences here in the jitter needed in order to do the hexagon task. And so basically what Cook argued is that even though she had her motor theory that we talked about earlier, Jen Cook basically said that the ability, she said that maybe this theory of mine, the motor theory, isn't entirely explanatory, and there is a lower level of explanation even beneath the motor theory, because the ability to move smoothly and fluidly may depend upon like a social processing mechanism where we have to watch other people move in order to move ourselves as such. That's how we learn, from watching other people, especially when we're an infant. And so beliefs about one's own movements are altered by perceptual signals during early development, which basically allows us to question whether the motor deficit comes first or whether the social perception deficit comes first. Again, is everyone with me? The idea is that if we don't perceive biological motion correctly in other people, then our own biological motion is going to develop atypically ourselves. And if we're contrasting the two explanations, like the motor theory and the perception theory, essentially motor atypicality theory, I think it's a great theory, but I think it lacks the power to explain quite a few symptoms, such as the visual illusions. What's that got to do with susceptibility to visual illusions? The sensory adaptation stuff and the sensory profile. So essentially, okay, it's cool, yeah, I really like the motor atypicality theory, but how is it explaining these hypo or hypersensitivity to certain stimuli in the environment? How is it explaining the fact that autistic people are really good at seeing through visual illusions? It lacks the power to do that. Whereas a low-level theory based on perceptual abnormality can explain all of these features. And then we can even look at it at a broader level, almost more computational and mathematical. But also, yeah, before we get into that, we can see that the perceptual theory may also explain things like insistence on sameness, repetitive movements, intolerance of uncertainty. Because as we said, with the perceptual theory, if their perception is say atypical in some way, then they're not seeing the difference between certain movements, for instance, or as Kanner said, they don't see things in their whole, so therefore they're far more likely to prefer something that they know. They're less likely to expand their behavioural repertoire because there's more uncertainty, there's more variability within the environment as such. So it explains these non-social features too. And as I said, if we wanted to look at this more computationally, then we can look at this Bayesian framework. So Bayesian maths comes from Thomas Bayes, who was a mathematician in the, I think, 1700s. And I won't go into the complex maths, it's like probability theory. But the idea is that it can be applied to autism research. This is, again, Pellicano and Burr, they're at UCL as well, both of them. And they basically argue that attenuated priors, hypopriors, may be responsible for unique perceptual experience of autistic people, which leads to the tendency to perceive the world more accurately rather than modulate by prior experience. So we said that autistic people are less susceptible to visual illusions, and it's because, I can explain this really simply, when we perceive the world, we always have information coming from the senses. I think I might have explained this in a previous lecture. We have information coming from the senses, and we have information, our expectations of the world, our knowledge of the world, how things work, our prior expectations. So our prior expectations are called hypopriors, what we know about the world already. And normally, as I said, these expectations influence our perception. We don't perceive the world veridically in terms of how it truly is, but we construct the world around us based on what we know about the world. So you can see it from these examples. There's no triangle here, but we expect to see a triangle. And you can see it here. This is the hollow face illusion, which is where we see a convex face staring out, but this is actually completely concave, and it's just the way that the contours and the shadows inside this concave hole in a wall are coming out that makes us seem like it's convex and coming outwards rather than inwards. And same, everyone's seen this illusion where these are exactly the same width and length, even though they look completely different because of how we perceive the world to be, depth perception, that type of thing. So every time, even in the world now, like as I said, I can see some of you are further behind other people, not because the input coming to my eye is purely on a 2D plane, but just because I can see that Sergei is behind Mekdes, but that's because I know that the lecture theatre slopes upwards and that someone has to sit behind someone else, essentially. So we always have these prior expectations of how the world works. And the idea is that typically we have to integrate these two in some way. You can see here, this is the hyperprior, this is the sensory information, and we kind of come out with like a compromise between the two of them. And what Pelicano and Burr are arguing is that the hyperpriors, our expectations and knowledge and understanding expectations of the world, in autism are really imprecise. We don't have any expectations about how the world works, so we rely far more on sensory information coming into our senses, which then prevents learning. Or the opposite thing is they have fine hyperpriors, but somehow the sensory noise coming into the autistic person's brain is like viewed extremely precisely. But either way, it leads to differences in how stimuli are processed compared to neurotypical people, because there's less reliance on these top-down expectations or knowledge of the world, and more reliance on the sensory input. Yeah, I might have explained that really badly, but if anyone has any questions, please let me know. That's the suggested reading. And I just want to say thanks for attending this course. I've really enjoyed doing it, and yeah, you've all been fantastic students, and yeah, I hope to keep in touch. But you can if you want, that's my email, and I know some of you have other ways of contacting me.